So, morning everyone. We now move on to a series of 2 lectures on, possibly 3 if this stretches too much, on variational autoencoders. What we've seen so far are that neural networks are great as generative models. We've seen how they can do classification or regression. We've seen different models which can do this, like MLPs, convolutional networks, recurrent networks, and in the next series of 4 lectures, including these two, we will be talking, actually the next series of several lectures, we will be talking about neural networks as generative models that can model the distribution of any data so that we can draw samples from these distributions. So, but first, before we begin talking about modeling generative distributions and drawing samples from it, generative models and drawing samples from it, what is a generative model? So today's lecture is going to be focusing primarily on what generative models are and how we estimate them. So here is, I have a lot of slides. If things go too fast for you, again, as always, please stop me and ask questions, right? This is going to be a fast lecture. Now, what is a generative model? A generative model is a model for the probability distribution of some data, like a multinomial distribution. That is a generative model, or a Gaussian. From a computational perspective, you can think of a generative model as this box, which when poked with some random seed will generate data. And so if you want a generative model for some data X, then this box will generate data such that the distribution of the data that it generates will match the distribution of the data that you're trying to model as closely as possible. So in either case, it's a probability distribution which can be parameterized, and you can write a function for it. And now a lot of the magic in machine learning and deep learning is trying to figure out, come up with an appropriate generative model for the data that you observe so that you can explain its statistical properties and you can make predictions about it. And this is not a new task. We've had millennia of coming up with some possibly very absurd generative models. Anyway, here are some examples of generative models that you guys are familiar with. The multinomial probability mass function, like a dice. A dice has 6 faces. Each of the 6 faces has a different probability. Now, if I roll a dice n times, then what is the probability that I will get the number 1 once, the number 2 7 times, the number 3 6 times, 4 5 times? So the probability of getting a specific set of counts for each of the faces of the dice from a certain number of rolls, that is a multinomial distribution. And it has parameters. The parameters are the probabilities we assign to the 6 faces of the dice. So this is a multinomial probability mass function. That's a generative model. It is parameterized, and the parameters are the probabilities of the individual outcomes. Or, for example, if you have discrete data and you can have where the discrete data can take any number of uncountable but infinite number of values, in that case, you would have other kinds of generative models, like the Poisson model, where the probability that a random variable x takes the value k is given by this exponential formula here and has this distribution. Again, this is a generative model for discrete data, numeric data in this case, and it is parameterized by a single value, lambda. You're also familiar with Gaussians. Everybody knows what a Gaussian distribution is. It's this bell-shaped distribution, which is parameterized entirely by its mean and its variance. And the shape of the distribution itself looks something like this. It's the shape of a bell. These are all things we are familiar with. So now, the problem in all of these tasks is you're given some data x, and we decide, based on whatever intuition we might have, that the probability distribution for this data follows some model p of x theta. And so now when we try to learn the generative model for this data, then the problem is that of estimating this parameter theta such that it best fits our observations x. And the hope here, the training data that we have, and the hope here is that when we learn this model to fit our data, then it will also represent data outside of the training set from the same source. And so here are some examples. Now, consider that a guy rolls a dice, a six-sided dice, many times. So obviously the distribution is multinomial. And at the end of it all, he plots a histogram for the number of times each face turned up. So n1 is the number of times he got 1, n2 is the number of times he got 2, and so on. So here is the distribution, the histogram that he has plotted. Now, if he were given the choice that this dice it's loaded, it's not fair, and that it either has this probability distribution for the 6 faces or this one. Given that this is the histogram of outcomes that he has observed, which of these two do you think is the actual probability distribution for the dice? Anyone? Somebody want to take a guess? Speak up, guys. Utter silence.
They're equally likely.
Why would you say that?
Well, because we only get the proper distribution as n goes to infinity, so any of these distributions might make sense.
Just given this, what would you, oh my good God, my laptop's gone to spinning mode. So yes.
The bottom one, the green one.
Yeah. Now, I can't believe this. My laptop has gone into spinning mode. Okay, it's woken up. Or let me give you another example. We get a collection of numbers, and these are actually real data from if you plot the histogram of the zeroth capstone component from your homework 1, for example, you'd find the histogram looks just like this. In fact, this is exactly what it is. These are capstone coefficients from some speech data. Now, this distribution looks vaguely bell-shaped. If I were to decide that I'm going to model this distribution using a Gaussian, I have the choice of these 3 Gaussians, the yellow, the red, and the green. Which do you think best models this distribution? Which
the red one.
The red one, right? So yeah. So what is the reason we chose the red one over here? Or in this case, what is the reason we chose the one at the bottom?
It's closer to what we see in history. It
kind of fits what we see better, right? So we are speaking of a notion of a fit. But then what exactly, it's very obvious to you visually what it means, which one matches best. But there's an underlying assumption that you made when you chose either the red one or the lower one over here. And what is this assumption? First, we are assuming that the data are generated by draws from the distribution. And the second one, the most important assumption here that we make is that the world is a really, really boring place. It means that everything that you have, that you observe, is very typical. It's that there's nothing unusual about what you have observed. And so the consequence of this world is a boring place assumption is that the data that you got is typical of the distribution. And so which of these 3 distributions for which of these 3 distributions is this data more typical? Clearly the red one, right? Because it's assigning higher probability to the more likely events and lower probability to the less likely events. So we're going to sort of formulate the maximum likelihood estimate on this principle. We're going to select the distribution of all possible distributions that has the highest probability of generating the data. Of all the distributions in the world, for which distribution are these observations most typical? Which distribution makes my observation the most boring observation possible? That's the one that we actually choose. It's based on the world is a boring place principle. So let's apply this to a couple of different examples. Say multinomial distribution. We've got these, someone rolled a die, and here are the outcomes we got. Now, the maximum likelihood principle says you have some data X that you have observed. You assign some parametric distribution with parameters theta to it. In this case, the parameters are going to be the probabilities of the 6 faces of the dice. And so we are going to choose the parameters theta such that the probability assigned to the data by our model is maximized. Basically, you want to choose the distribution that makes the data most boring. And so makes your observations most boring, most typical. So you're choosing the probability distribution for which your data are most likely. In other words, when you choose the probability distribution, because you've already chosen the form of the distribution, what remains to be chosen are the parameters theta. You're going to choose theta to maximize p of x. Or alternately, we can maximize the log of the probability of the data. The log is a monotonic function. So this p of x theta is going to have its maximum value at exactly the same place where log of p of x theta is maximum, because log is monotonic. And so this is what we'll maximize. So if I wanted to find the maximum likelihood estimate for the dice over here, based on these observations, I'm going to find the set of faces, face probability, such that this term is maximized. So also for the Gaussian, if I want to find the maximum likelihood estimate of the Gaussian that explains this data best, then I'm going to compute the log probability of all of my observations as a function of the model parameters and find the theta that maximizes this probability. So here's what it's going to look like. In the case of the multinomial distribution, let's assume that you roll the data a certain number of times, you roll the dice a certain number of times. And so you get a large number of outcomes. Each roll of the dice is an independent outcome. So the probability of the collection of outcomes that you got is the product of the probability of the individual outcomes. So also here, the probability of the collection of outcomes that you got is the product of the probability of the individual outcomes. And we're going to choose these model parameters here, which are the probabilities of the faces, or over here, which are the mean and the variance of the Gaussian, such that this likelihood term here is maximized. And now, for the Gaussian, p of x, the probability of any given observation is a Gaussian. In the case of a multinomial distribution, if I've got, say, outcomes 1, I rolled the dice, I got 1, 1, 3, 6, 5, 2, 1, and so on, then the product of the set of outcomes is p of 1 times p of 1 times p of 3 times p of 6, and so on. And I can write this as generally as the probability of 1 raised to the number of times 1 occurred times the probability of 2 raised to the number of times 2 occurred, and so on. So this term here, the log probability of this data is the product over all possible outcomes of the probability of the outcome raised to the number of times it happened. Similarly, the probability of any individual observation here is simply going to be the Gaussian computed at that value x. And so I can actually expand out the log. Thus, when I take a log of a product, this becomes the sum of a log in both cases. And so this is going to be the sum over all possible outcomes of the number of times the outcome was seen times the log of the probability of the outcome itself. Now, in your experiment, this number is given. You know exactly how many times each outcome was observed. This term p is what you don't know. This is the parameter of the distribution. So you're going to try to estimate these probability terms such that this term here is maximized. I won't go through the math. It's very easy to solve. It's a simple differentiation and setting the derivative to 0. And that will give you the solution for the probability of the ith phase. The probability of the ith phase is the number of times it was observed divided by the total number of observations. So also for the Gaussian, if I just, the log probability of all of my observations is the sum over all observations of the log of the Gaussian computed at the observation x. What you have are these terms x. You don't have the mean and the variance. So this ends up being a function of the mean and the variance. You can optimize this term here with respect to mu and sigma squared by differentiating it and setting it to 0. And when you solve for it, you end up with these estimates for the mean and the variance. The mean for example, the maximum likelihood estimate for the mean, for example, is simply the average of all of the samples that you have observed. Now, I haven't gone through the math. I'm sort of glossing over the math. These are just the basic ideas, and hopefully you guys are familiar with it. Even if you're not, there shouldn't be anything particularly mysterious about what I just said. So if you have got everything we've spoken so far, please raise your hands. I'd like to see. So I'll wait. If only 40 out of 94 people have raised their hands, other 50 have not. What are your questions? Any questions, guys?
For the Gaussian distribution, why we don't need to multiply each term by x here?
So here it is, right? Let's just do this with for the Gaussian. I've got a bunch of observations, x1, x2, and so on. So the probability of my observations is p of x1 times p of x2, right? Which is going to be the product over all observations of the Gaussian of x at mu sigma squared, right? You with me? So when I take a log of my training data, this is going to be the summation over x. And the Gaussian, of course, is given by 1 over square root of 2 pi sigma squared, exponent of minus half x minus mu whole squared by sigma squared. This is, I'm assuming it's a scalar. So this is, if I take the log of this, I get the log of this term. For now, I'll just say something here. I'm focusing on the mean plus minus half of x minus mean whole squared by sigma squared. So you with me here so far?
Yes.
Okay, let me erase this. So if this is what I'm going to be maximizing, right? So to maximize it, I'm going to be doing this d log term over d mu, which is going to be summation over x. This is not a function of mu, so that goes away. I have the minus half here, then 2 times x minus mu whole squared by sigma squared, and I'm going to set this equal to 0. This 2 and minus half go away because you're equating this to 0, right? And so erase this from my last class. And so if I write that, that's going to give me summation x. Actually, there's no square. X minus mu over sigma squared equals 0. I can ignore the sigma squared, which says summation x minus mu equals 0, right? Just working this out very trivially. And which says summation over x equals n times mu. And from this, you're going to end up with a solution. So basically, we just solved the what we were given pretty directly. We didn't do anything fancy with it. Does that make sense?
Yes.
Okay. So why is the canvas not clear? The point is here that what we really did was we tried to find the parameters of the distribution that maximize the probability of what we saw, because that makes the data that we saw the most important. There's a poll here, Kushal. Okay, 5 seconds, everyone. Okay, stop it. Let's stop the poll. Obviously, both are true, right? So here's the situation with maximum likelihood estimate. We know how to do it. But then there are many situations where the data you get are incomplete. So they are insufficient to estimate your model parameters directly. This could be because the data have missing components, or because the structure of the, I'm saying network, or the model causes issues. So let's consider this first instance here, where the data have missing components. For example, let's say we've just seen how to compute the parameters of a Gaussian distribution. Easy, right? This we already know. And these formulae hold regardless of whether your data are scalars or they are vectors. The formula for the mean is always going to come out to be the average of all of the observations that you got. That is your maximum likelihood estimate. So now, suppose instead that you got a collection of these vectors. You know they're Gaussian. You're going to try to estimate the parameters of this Gaussian. But for some reason, some components of the data are missing. So for example, the census board. The census board takes census and people are made to fill out forms. And they ask you all kinds of things. How much do you earn? Where are you from? Blah, blah, blah. And some people won't fill in some details. For example, not everybody's happy telling you their income. Not everybody's happy telling you maybe their health status, right? So you have these vectors where some components are missing, and the components that are missing are different for each vector. This guy didn't want to tell you his educational status. This guy didn't want to tell you his income. So now you have this collection of data with incomplete missing components, and from this you have to estimate the Gaussian. So we have a problem, because the maximum likelihood formulation that we saw works when you have the complete vector. So what we did over there is that you assumed you had a collection of complete data, and so you could try to estimate the mean and the variance to maximize the log likelihood of the entire data set where each vector was assumed to be complete. And this we know how to solve. The problem is we cannot compute log of p of x because x, which is this complete vector, has many components missing. By missing, I don't mean their values are 0. I mean we don't know what their values are. They could be anything, right? So here's the situation. These are the data that we actually have. The green components, those are the ones that are provided to us. And these are the data that are missing, right? So again, another situation where you can have something of this kind, for instance, is movie ratings. When Netflix gives you ratings for movies, you sort of download some movie and you say, it says you might have liked these other movies. Where did it get it from? Every person rates movies. There are millions of movies out there, and you've watched maybe 1,000 of them, and you've provided ratings for those 1,000. So this vector of movie ratings is very sparse. You filled in 1,000 numbers, the remaining are all black, and you have this for millions of people. And from these large collection of incomplete vectors, it learns a Gaussian, and then based on the numbers you do provide, the movies that you do rate, it predicts the ratings of the movies that you didn't see. So once again, you have incomplete data, and all of these things are missing, and you have to learn the Gaussian from these incomplete data. So here is what we have. The green set, these are our incomplete vectors. I'm calling them O's. The missing components I'm calling M's. And the complete vector for any particular vector is going to be the combination of the observed components O and the missing components M. Again, the complete data are not available. All you have are these observed components. And you must estimate the parameters of the distribution. And our log likelihood, now, if you want to perform maximum likelihood estimation, you want to maximize the likelihood of what you did observe, which means that you want to maximize the likelihood of these green components because this is all you have observed. This is the only data about which you can make the assumption of boringness. These black components have not been observed, right? So your maximum likelihood estimate is going to have to maximize the log likelihood of the observed data, the green components. That's all you have observed. And unfortunately, when you write out the Gaussian formula is over the entire vector, not just over the green components. So what do we do? For every vector, I can sort of separate out the observed. I can write a vector has many components, so I can write the probability distribution in terms of all of the individual components. So the vector has observed components O and missing components M. To get the probability of the observed components, I have to marginalize out the missing components by integrating them out. And now I get the log probability of the entire observed training data, where the probability for the individual vectors, the observed components of the individual vectors, is obtained by computing the Gaussian over the entire vector, including the missing components, and then integrating the missing components out. And so now, when you want to perform this maximum likelihood estimation of the Gaussian parameters, you have this nasty situation here, where you're trying to find the mean and the variance terms, such that this term here is maximized, but this term has a nasty integral inside the log. And that's not going to be easily solvable. In fact, in this case, it's not. So we have a situation, right? Here's the second one. Read this network as model over here, right? So you can have missing components because of the structure of the model. Now, how many of you are familiar with the notion of a Gaussian mixture? Raise your hands. Not very many, apparently. So a Gaussian mixture distribution is a fairly simple idea. Let's say I have some data, and let's say if I plotted the histogram of the data looks something like this. This is clearly not Gaussian, right? And so how do I parameterize this? What I can say is that this distribution is the sum of many Gaussians, that there are several Gaussians over here, and that the distribution itself is the sum of these Gaussians. And when I add them up, I'm going to get something like this, right? I'm going to get something like this, which kind of fits this guy over here. So the probability of any x is going to be some, A1 times Gaussian of x with mean 1 and variance 1, plus some A2 Gaussian of the data with mean 2 and variance 2, and so on. So these A's, these are actually the probability of the Gaussian. You can think of this as the proportion of the Gaussian, right? I can also call this P of k for the kth Gaussian. This is the kth Gaussian itself, and you're getting a weighted sum of these 4 Gaussians, which will fit the probability distribution of your data. In Gaussian mixture models, I can generally write this as P of x equals summation over k are all the Gaussians that you're adding. P of k is the proportion of the Gaussian times the Gaussian of x with mu k and sigma k squared as parameters. This is the standard representation of the Gaussian mixture distribution. The parameters of this distribution are these proportions and the means and the variances of the individual Gaussians. Now, which is what we've got here. A Gaussian mixture distribution can model fairly complex distributions. There's a generative story behind Gaussian mixtures. So the generative model behind Gaussian mixtures is that there's this box, and inside this box is this generative character who has many different Gaussians at his disposal. In order to generate a single observation, he first selects one of these Gaussians and then draws a vector from that Gaussian. So the probability that the guy will generate any vector x is going to be the sum over all of the Gaussians of the probability that he will select that Gaussian times the probability that he generates the particular vector x from the selected Gaussian. So this is the generative model, and there's a two-step process. This character, the generator, first he selects the Gaussian and then he draws the vector x from the Gaussian. So the process of generation requires the drawing of two variables. The first is the Gaussian and the second is the observation itself. And so the process actually draws two variables for every observation. First, the Gaussian, and the second is the observation from the chosen Gaussian. So the probability of choosing one particular path over here is the probability of choosing the Gaussian and drawing the observation from it, which is P of k comma O, which is P of k times the probability of O given the kth Gaussian. Now, if all you're observing is the final outcome and you don't know which Gaussian he has chosen, then you marginalize out the Gaussian itself by summing over the Gaussians, right? So this is how a Gaussian mixture model models the distribution. But now I'm only giving you a collection of observations. So is this clear to everybody? Raise your hands. Okay, good enough, right? But now I'm only given a collection of observations, O. Now here is the story. When you have a generative model of this kind, in order to be able to estimate all of the parameters of the distribution, you need to know the complete sequence of steps that the generator followed in generating every single observation. If the complete sequence of steps is not available to you, some data are missing. Here, for example, the complete sequence of steps means you need to know the Gaussian chosen for each observation and the observation itself. So in the ideal data, for every observation training instance that you got, you would also know which Gaussian the data was drawn from. So if you have green, red, and blue Gaussians, then you would know that the generator, in drawing this first vector, first chose the blue Gaussian and then drew the observation from it. And then for the second one, maybe it chose the red Gaussian and then drew the observation from it. If you have all of this information, then estimating all of the parameters of the model is easy. I can just segregate out all of the vectors that came from the blue Gaussian. And from these vectors, we know all of these came from the blue Gaussian. I can estimate the mean and the variance of the blue Gaussian simply by, the mean is the average, the formula. Similarly, I can segregate out all of the vectors that came from the red Gaussian, and I can estimate the mean and the variance of the red Gaussian from these data. And I can segregate out the vectors that came from the green Gaussian, and I can estimate the parameters of the green Gaussian. The problem is that when you get your training data, the actual Gaussian from which each vector was drawn is not known. So you're missing the identity of the Gaussian that was used to generate the data. You're missing the color of the Gaussian in our example. So what we want is a combination of O and K. K is which Gaussian the data was drawn from, and O is the observation itself. What you have is just the sequence of observations. So this means our data are incomplete. Now, again, if you want to perform the maximum likelihood estimation, you want to compute the parameters of all of the Gaussians such that the total log likelihood of the observed data is maximized. So summation over O, log of P of O. The probability of any individual vector is the summation over all Gaussians of the joint probability of the Gaussian and the observation. Why so? Because we are missing this information K. So we're basically marginalizing K out of this distribution. This is very analogous to the case where we were trying to estimate a single Gaussian from vectors with missing components. It's no different. It's the same problem. And for this, of course, we know the formula. And so when you actually write down the maximum likelihood estimate, You have to learn, estimate all of these means and variances for all of the Gaussians of this term, which sums over all observations of the log of this ugly term here, which has a summation inside the log. And the summation happens because we are trying to marginalize out the Gaussian itself, because we didn't know which Gaussian the generative process actually selected in order to draw each observation. And anytime you have the log of a sum, then directly optimizing something of this kind can be very challenging, and in fact, best avoided, right? So here's the general form of the problem. When you have missing data or variables in your observations, then and where your generative model itself, learning your generative model requires knowledge of these missing variables, then in order to compute the probability of what you do have, you have to marginalize out these missing data or variables. And so this results, so if I'm generally representing these missing variables as the term h, I've switched from m to h because the popular term is hidden. If I'm so if I've got these missing variables h, and what you've observed is O, then in order to compute the probability of O, you have to marginalize out h by summing or integrating over all h. And so the log probability of an observation is the log of the sum or integral. And this term is what you have to maximize in order to come up with a maximum likelihood estimate of the parameters of the distribution. And having a log of a sum or an integral makes this estimation challenging, to say the least. And you will not find closed form solutions. You need iterative algorithms. And so what we will try to do, so this is the general layout of the problem that we're going to be dealing with in the next couple of classes. And so what we will try to do is to get an approximation to this term over here, which is the log of a summation that is more tractable than this term itself. And we will try to maximize this approximation. So this is our problem. And for this, we are going to be using an algorithm called expectation maximization. So at this point, I believe we may have okay. So here's how expectation maximization works. There's some ugly formula over here, but I'm going to try to explain this. By the way, is everybody with me so far? Raise your hands if you are. Okay, good. So here's how expectation maximization works. Now, we have a maximum likelihood estimation problem. You're trying to estimate the parameter theta. You have the log of p of x semicolon theta. You have your log likelihood of your data. And so the log likelihood of the data as a function of theta is going to be something ugly like this, right? Or let me make it less ugly. Functions definitely don't fold back. It's going to be something ugly like this. And we want to find the theta which maximizes this guy, right? This is our maximum likelihood estimate of theta. We want to find this guy. Our problem is this function, because we have the log of a sum, this function is hideous. And so you can't really directly solve for it. So here's what we will do. We will come up with a function that's always a lower bound on this log likelihood. What do you mean by this lower bound? It means that this function has this property that is going to always lie below this guy. It will never, ever exceed it. But then we are going to construct something called an elbow, which is an empirical lower bound. And the elbow, the manner in which we will construct it, this function has a very interesting property. This function has this interesting property that while it is guaranteed to be a lower bound, you can control this function such that it touches the log likelihood function itself at a point of your choosing, right? So we have our ability to make this lower bound function touch the log likelihood function at a point of your choice. And so now we will start off with some initial estimate, and we call this theta 0. Then I'm going to construct my elbow to touch my log likelihood function at theta 0. So my elbow might be something like this. Then having done so, I'm going to maximize the elbow. The elbows will be a nice clean function which is easily maximizable. And so when I maximize my elbow, the maximum of the elbow is over here. So my elbow function gets maximized at this point. Now here's what I know. At this point, the elbow function that I've got, because I'm maximizing it, this value is going to be greater than this value because I'm maximizing my elbow, right? So this guy is greater than here. But because it's a lower bound, this also means that this guy is greater than this one, right? So having done that now, so everybody with me so far, raise your hands if you get this. All right, very nice, right? So what will I do? I call this my first estimate theta 1. And then I'm going to redraw my elbow, except now it touches the log likelihood function over here. And so now my elbow is going to be something like this. It touches it here. And now I can go back and maximize my elbow function again. And the new maximum is out here. So I call this theta 2. And I know that this guy is going to be greater than here. So therefore, this guy is also greater than here, greater than this value. Now I redraw my elbow function again, and I make it touch at this point. And I maximize my elbow. So if I keep repeating this process, where I make my elbow function touch the log likelihood function at a point of my choice, and then maximize the elbow, then redraw the elbow to touch the log likelihood function at this maximum, then maximize that. If I keep repeating the process, I'm guaranteed that at each step, the log likelihood of my data at the new estimate is definitely greater than or equal to the log likelihood at the previous estimate. And so as I keep going through these iterations, the overall log likelihood of my data keeps increasing. Now, the magic behind all of this is to be able to design such an empirical lower bound. Yes, Chian?
Is it possible? Could you go to the previous slide, please?
Previous slide or the picture?
Oh, the picture. Sorry.
Okay.
Is it possible that the elbow function, like the highest point, happens to be the same as like a, I guess like a local maxima?
Yes,
like,
that's exactly what we will do, right?
Oh,
Eventually, as you keep going here, you're going to end up out here, and then the only elbow function you can draw is this guy, right? And then you found your local maximum, and that's what you're going to do. There's no guarantee of finding a global maximum, but you're going to be finding the local maximum.
I was wondering what would happen if it kind of stopped, like before we reach theta.
It can't, right? By the definition of it. So I mean, you can always design a really crappy lower function, which is an elbow function, which does this something of this kind, right?
Oh.
And then it's going to stop before it hits the local maximum. It is possible. You're right. But in general, your elbow functions are not going to be of this kind. Particularly the one we use for EM doesn't have that property.
Okay, so we designed this function, and then we
Yes.
can kind of control. Okay, thank you.
And in fact, how we design it is on the slides. So you should go over the slides. But here is what the elbow function looks like for expectation maximization. So you're going to look, remember, our complete data are the union of the missing components H and the observed components O. And generally, if we are not trying to marginalize H out, you get the log of the complete data, and the log of the complete data is something that's tractable. That's something we can usually deal with. The problem really arises when we're trying to marginalize these missing components out. So the empirical lower bound for problems like these happens to be this one, where you take the the expectation of the log probability of the complete data with respect to the components that you have not observed. So which means this is the log of the joint P of the joint of H and O times the probability of H given O summed over all H. So this is the expectation with respect to the missing components or conditioned on what you observed of the log probability of the complete data. And this outside term is computed using your current estimate of your model parameters, and you're going to be estimating this value theta. So what this guy does here is, again, it's mathematically provable. You take the P of H given, let me erase this so I can write. So P of H given O theta K, that is taken using the current estimate, and the log of P of O comma H semicolon theta, that is this variable theta that you can maximize with respect to find the next guy. So this is guaranteed to be an empirical lower bound, and you can use this within the, there's a second term, there's a constant term. So this is the entire elbow, but it's sufficient to maximize the first guy because the second is not a function of theta. Anyway, so this is what we will maximize, and repeatedly maximizing this guy is guaranteed to find you some kind of a local maximum. So that's your expectation maximization algorithm. You're going to initialize your estimate for the parameters, then you iterate until the log likelihood of your observed data converges. And what do you iterate at each step? You compute the a posteriori probability of the distribution of the missing components given the observed components. And from that, you compute this term here, the expected log likelihood of the complete data. That is the expectation step. And then you maximize the expected log likelihood of the complete data to get the next estimate for your parameters. This entire thing is expectation maximization. And so that's a lot of math, right? What exactly are we doing? Math is all very nice. Practically speaking, how does this translate to an actual procedure? So we'll look at that, but at this point there is a poll. So Kushal, can you pull up the poll? So this was the first poll for those who can't watch in the video. And this is the current poll. "15 seconds, guys." Okay, let's start. So here, going back, for the first question, EM is an iterative algorithm. We just saw that. It does iteratively maximize an elbow function. The fact that it's iterative means there is no guaranteed closed form. There is no closed form. In fact, even maximizing this local elbow function could itself not have a closed form. It's just, all it means is that maximizing the elbow function is typically simpler than maximizing the original function itself, right? So this third bullet is not true. Also, the elbow is a lower bound on the actual log probability of the training data, as we just saw. It's a function of the model parameters, as we also saw. And because it's a lower bound, it can never be greater than the log probability of the training data. It is a lower bound. The best it can do is to be equal to the log probability of the training data. So, and it is in fact the expected value of the log probability of the complete training data, including both observed and missing components, where the expectation is taken with respect to the missing components using the current estimate of model parameters. So all fine. Math is great. What does it really do, right? So I'm going to be looking at these two cases again. Let's look at the first case where the data themselves have missing components. Now, recall this. This is where we were trying to estimate a Gaussian with incomplete vectors. We had all of this data, but then for each vector, we only had the green components, the black components were missing. Now, in this case, what are the complete data? The complete data is going to be the union of the observed data O and the missing data, missing components M. So each vector is going to be the combination of the green and the black. The green are the O, the black are the M, right? So consider just one vector. Let's say this first guy. What I am going to try to do is to try to complete the data. I'm going to try to fill in this missing vector, right? But then, what is the value that this missing vector can take? Is it unique? Given only these guys, is there only one value that this missing vector can take? Anybody? Missing component. So maybe this is not very clear, right? Let me give you a trivial example. Let's say you have people in the world. People can be, male or female, and people can be tall or short. Now, on average, 50% of people are female. 50% of people are tall, right? So, but then if I want to compute this probability distribution over here, I need a bunch of training data for which I need the gender of the person and I need the height of the person. If I get all of these, if you give me the gender and height for lots and lots of people, then I can compute the entire probability distribution. What is the probability that you have tall male people? What is the probability that you have tall female people, etc. Right? But then let me give you this thing. Suppose I give you a person's height, a person's gender. I tell you the person is male. And then I ask you, what is the value of their height? Is this answer unique? Anyone?
No.
No, right? So suppose I told you from here that amongst females, 2/3 of people are short and 1/3 of people are tall, right? So P of height given female is 1/3 for tall, 2/3 for short, okay? Similarly, P of height given male is 2/3 tall, 1/3 short. Suppose this is not necessarily true, but suppose I gave you this, right? And then I gave you an example where I told you the person was male, right? You cannot make a unique decision as to what the person's height was, correct? But then suppose I give you 1 million examples of the same data. I've basically cloned the data where I've cloned the gender. So all of these are male. Then can you tell me what fraction of these are going to be tall males and what fraction of these are going to be short males?
Yes.
What will these be?
They should start to approach the 1/3, 2/3.
So 2/3 would be tall and 1/3 would be short, right? So going back to this answer, so similarly, in the case of a Gaussian, right? Yeah. Suppose, assume that I have a Gaussian on 2 dimensions. And so the Gaussian is going to look like a ball, like a bell-shaped figure. Now, this is x1 and this is x2. Now, I give you x1. I tell you x1 is this. At that x1, is x2 unique?
No.
No. Okay. So what will it be like?
It'll be a
If I give,
Gaussian.
yeah, if I give you x1, it's like slicing this bell at that value of x1, right? If I slice it, that slice is going to have this face, and that face, if I look at it face on, is also going to be Gaussian, right? And this is P of x2 given x1. Everybody with me? Raise your hands if you're with me. Okay, great. So here's what I'm going to do. I'm going to try to fill this vector, fill this missing component, but I know that the answer is not unique, right? There isn't just a single value for that missing component. That missing component can take many values. Specifically, for example, if I gave you this particular value of x1, then this value of x2 is going to be very likely. This value of x2 is going to be less likely. This value of x2 is going to be even less likely. This value of x2 is going to be very less likely. This value of x2 is going to be impossible. So the different values of x2 for any given x1 have different probabilities, and that probability is going to be P of x2 given x1. So what I will do is to make a very large number of clones, 10 into infinity, of this one data instance. And then I'm going to I'm going to complete the data in every possible way. But then I'm going to complete the data with all possible values of this missing component in proportion to how frequently I expect to see it. So going back here, if somebody gave me this data, I'm going to try to complete it by making many clones of it, but in 2/3 of them I'm going to write tall, and in 1/3 of them I'm going to write short. That's how I've completed it. Was that clear to everybody? Raise your hands.
So you're going to randomly pick 1/3 of them and cut it short, and then 2/3 of tall?
Yeah. I'm
Okay.
actually completing the data.
Okay, but there's no preference in terms of how you color the data, or how you assign the labels to the data.
Yeah. So again, this is kind of, they're not labels, right? These are incomplete data. I'm just trying to, I know how to compute the probability distribution given the completed data. So the first thing I will do is to complete the data. And I will complete the data in a statistically reasonable way.
Okay.
Make sense, right?
Yeah.
And so what I'm going to do is to fill it with every possible value of the missing component, but the number of times any value occurs is going to be in proportion to the a posteriori probability of that value given the observed data, right? And so this is what I'm going to do. I'm going to complete the vector by filling the missing components with every possible value, but assign a proportion to each value, which is proportion to P of m given O. And P of m given O, the a posteriori probability of any missing value given the observed value, can be computed if I know the joint probability. This is where the math kicks in, right? P of O given m. And so assume that you have it for now, okay? So here's what is going to happen. For every one of these vectors, I'm going to fill in the missing components in every possible way. So this one vector is going to expand out to all of these clones. This one vector is going to expand out to all of these clones. This third vector is going to expand out to all of these clones. And so now I've expanded my data into a very, very, very large set where every data vector is now complete. But then the completion when I've completed them, the values I've filled in are in proportion to the statistical expectation of how frequent that value happens given what you have observed. So everybody with me so far? Raise your hands. And now it's easy, right? So this P of m given O, this is where the iterative process comes in. This comes from a previous estimate of the model. And now I have complete data, right? If I have complete data, it's very easy. I have complete data. Every observation, I have lots and 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 lots of complete data. So I can estimate my mean as 1 over n summation I complete data. These are complete data, which is to say 1 over n summation I or I mi, because these are the observed components and this is the filled in missing component, right? But then here is something that you come in. This completes this block of the completed data all have the same observed component, right? The first block comes from the first guy here. So this block of missing data, completed data, all came from the first vector. And so when I write out the formula for this, if I just take what I get over here, the summation, the O is going to be constant, right? So let's say, let's ignore the, actually no, let me be more explicit. So let's say when I completed the data, I cloned each data vector some large number m times, right? So when I do that, this block has size m. So I can keep, so there's an m over here. And the missing observed component, when I sum it up, is just going to be m times o. Correct? Everybody with me? Or did I lose you? Right. What will this missing component be when I sum up over this block? Anyone? So what will happen? There are a total of m clones. Of these m clones, the missing component m1 took the value m1 with probability m1 given O, right? It took the value. So this fraction of all of these is going to take the value m1. P of m2 given O is the fraction of this entire block that took the value m2. P of m3 given O is the fraction of this block that took the value m3, and so on. So I can write this generally as 1 over m. It's actually an integral, but it's an integral of P of m given O times m. Yeah, right? So did this make sense to you guys? Questions? Any questions?
So this is the
sorry, but how do we obtain this this previous estimate of the statistical proportions?
So remember, so again, you started with some initial estimate for the statistical parameters, right? So if you start off with an initial estimate for the parameters, this function P of n given O will have a closed form using those values.
Okay, so okay, it's kind of like part of the assumptions that we made.
Yeah, so this is and the math. I'm not actually working on the math, but here is because there's something much more fun than this particular process here, which is this. Guys, I'm again going to go over. I'm so sorry, but we'll stop at 9:20, let you guys leave, and then I'll complete this. I need to. So here is, so that is the formula, right? I'm going to be summing over all of the observations because each O occurs once. But for each O, I'm computing, taking the expectation over all possible values of the missing component of the missing. And so this xi of m is basically the completed vector, right? So when I take the sum of this block here, I'm basically or when I take the average of this block over here, I'm taking the average of all of the completed vectors. And in all of the completed vectors, the observed component is going to remain fixed. but the missing component is going to occur in proportion to P of M given O times. So this guy here, this formula here is basically taking the average of all of these values where the observed components are all identical, but the missing component occurs in takes different values, different proportions of the time. Same thing with the variance. And so the expectation maximization algorithm is going to be something like this. You initialize your parameters, and then until the log probability of your observed data converges, you using the current estimate of the parameters, you sort of fill out the missing components and then expand the data out and then re-estimate your parameters using the completed data. So this was the case where I had Gaussian data with missing components. This may not be very clear to you, the exact math of it, but there's a different way of doing this, which will be much, much simpler. And we'll see this in a few minutes. But then let me switch to the second example, the case of the Gaussian mixtures. In the case of the Gaussian mixtures, again, for each vector, the color of the Gaussian that the vector came from was missing, right? For each vector, we want the combination of the observed data and the Gaussian color of the Gaussian. Instead, what we have is just the vector O. And so what we observe is that, if I give you this vector O, I don't know which Gaussian generated it. I'm going to expand it out, and I'm going to fill in this missing component with every possible. I'm going to fill in this Gaussian value. I'm going to fill in the identity of the Gaussian that generated the data. But then, a vector could have been generated by any of these Gaussians. For example, if you had a vector out here, the blue, the red, and the green Gaussians all are capable of generating it, but with different probabilities. So what we will do is we're going to ask ourselves the same question. If we saw a very large number of these vectors, how many of them would have come from each Gaussian? And so we're going to fill in these Gaussian colors in proportion to the a posteriori probability of the Gaussian given the observation, right? Again, so if you look at this, for example, if this were the Gaussian, if my if my distribution had these three Gaussians, this blue Gaussian, this red Gaussian, and say this green Gaussian, right? Then if my observation were out here, then I know that it could have come from the red, green, and blue Gaussian, all of them. But then the red Gaussian is, at this point, the red Gaussian is much more likely to have generated this observation than either the green or the blue, right? And so when I fill in these colors, I will have many more reds than I will have greens or blues. Basically, I'm going to fill in these colors in proportion to P of K given now. And now I've completed the data by filling in this color. I'm going to estimate the parameters using the complete data. And of course, to compute P of K given O, we need to know we need to be able to compute this guy. This can be obtained if we know P of K and P of O given K, which is the proportions of the Gaussians and the parameters of the Gaussians, which we don't know, but we have the previous estimate in an iterative estimator. We can get these from the previous estimate of the model, and you use these to fill in the colors. And then once you have filled in the colors, so every data vector is going to get expanded out into a large set where these Gaussian colors, the Gaussian identities, have been filled in every possible way, except that each Gaussian is going to be filled in, the number of times it has been filled in is in proportion to the a posteriori probability of the Gaussian itself. Here, although I've only shown 3 bars, you've got to imagine that there's a very large number of repetitions where the number of times blue occurs is in proportion to P of blue given O, and so on. And now that we've got these completed data, I can pull out all of the blue vectors, and then I can re-estimate the parameters of the blue Gaussian from here. I can pull out all the green vectors. I can re-estimate the parameters of the green Gaussian. I can pull out all of the red vectors. I can estimate the parameters of the red Gaussian, and it turns out that we have nice closed form solutions for it. If you work out the math, once you understand what's happening, it's very trivial. So for any observation O, the number of blue vectors is going to be proportional to P of blue given O, right? So this is the total number of blue vectors that came from the first guy, and so on. And then we can re-estimate our parameters. Now, again, I'm not focusing on the formulae over here because we're going to look at the simpler way of doing EM. This is just to give you the standard mechanism for doing EM. You're going to initialize your data, your model parameters. Then you're going to complete the data in every possible way by filling in the missing information in proportion to the a posteriori probability of the missing components. And then now that you have the completed data, you can segregate the data out into the individual Gaussians and re-estimate the parameters for the Gaussians. So this is your EM algorithm. So the general EM principle, you complete the data by considering every possible value for the missing data and variables, which is in proportion to their posterior probability given the observation, and then re-estimate parameters from the completed data. So the key here was that when you had, regardless of whether you had these vectors from which you were trying to estimate a Gaussian and the vectors had missing components, or whether you were trying to estimate a Gaussian mixture where for each vector, for each observation, you were missing the color of the Gaussian, what we did was to complete the data. And we completed the data by filling in the missing components in proportion to their a posteriori probability, and then re-estimated the model parameters using the completed data, because once you have complete data, then we know how to estimate these parameters. It's easy, right? So this is the EM algorithm. Start with some initial estimate for the parameters, then use those to complete your data, and then re-estimate your parameters using the completed data, right? Now here's the key piece. The math seemed kind of tedious, right? But then there's something else you can do. You don't need to work out the math. Consider this guy. Let's consider the case of trying to estimate Gaussians with, from data with missing components. What I can do is to get the formula for P of M given O. This I can get in closed form using it doesn't even have to be closed form, but this I can get using the current estimate of the model parameters. And then from this, I can randomly sample M, the missing values, some large number of M times. And so when I sample it, this guy is going to get filled in with different values. And each of these values has been obtained by sampling this distribution. And so I can fill in the missing values by, instead of trying to work out the mathematical formulae, I can fill in the missing values by sampling this a posteriori probability distribution to complete the data. I can do this in both cases. So in the Gaussian case, what I would do is I have this vector. I don't know which Gaussian it came from, but then I can compute the a posteriori probabilities of the Gaussians. This is a probability distribution. I can draw the color of the Gaussian from this guy by sampling this distribution repeatedly. And now I'm going to generate a whole bunch of samples where this missing component, where this missing value has been randomly drawn by randomly sampled from P of K given O. And now I can complete this data through this random sampling process and then re-estimate my model parameters from the completed data. And so this gives us this new mechanism, which is also EM. You complete the data by sampling possible values for the missing data or the missing variables, and then re-estimate the parameters from the completed data, right? So here's the overall EM principle. Remember this is very key. We're going to initialize our model parameters. If you were just estimating a Gaussian, you're going to estimate the means and variances, initialize means and variances for the Gaussian. If it's a Gaussian mixture, you'd be initializing means and variances and the proportions for all of the Gaussians. Then we're going to iterate. In each iteration, for every incomplete data vector, we are going to complete the data vector by filling in the missing values in accordance to the a posteriori probability P of M given O as obtained from the current model. This can be done by either explicitly considering every possible value and getting this posterior based proportionality. That is the general expectation maximization algorithm that you guys are familiar with likely, or simply by sampling the posterior probability distribution P of M given O. And so now that you've completed this, you can re-estimate the model parameters from the completed data. And so this is the key of the expectation maximization algorithm, right? And so questions so far. There's a poll. Kushal, can you pull up the poll? Here. So wait, so guys, here is the 10 seconds, guys. Yeah. Okay, stop. So I think I might have filled in this poll wrong. There are 3 answers which are correct. The 4th one is wrong, right? So here, what we do is that in each iteration, EM is iterative. In each iteration, we complete the data by filling in the missing components or variables, and we estimate the parameters from the entire completed data. Now, a data instance can be completed by filling in the missing terms with every possible value for the missing term, all infinite of them if there are infinite of them, in proportion to their a posteriori probability, given the observed components. Now, rather than filling them in with every theoretically possible value, you can also complete the data by randomly drawing samples of the missing components from their a posteriori probability distributions, given the observed components of the data. This filling in has to be done iteratively. In each iteration, you will have changed the probability distribution because you have updated your estimates. And so the next iteration, you have to redo the entire filling in process. So this 4th point is wrong. The data completion has to be repeated in every iteration of the EM algorithm. So questions, anybody? Any questions?
Yes, Professor.
Yeah.
Does this algorithm heavily depend on our first initialization?
Absolutely.
Okay.
Right. But do you understand how the EM algorithm works? Raise your hands if you do. So we're at 9:20. Half of you claim to have understood it, the other half have not. The other half who have not are going to have trouble with this week's quiz. So please post questions on Piazza. Now, I have to go through, I have a bunch more stuff to go through in this lecture. So I'm going to take a pause. If you have any questions, ask your questions, and I'll pause the recording. So I'm going to switch topics because we're jumping into the key. What we've done so far is lay the foundation to teach variational autoencoders. And VAEs are basically built on this principle of expectation maximization. But before we do VAEs, it's what is a VAE? To understand that, let's go back to something we're all very familiar with, principal component analysis. So principal component analysis, let's say you're given a centered set of data. All of these data points, the mean of the data is 0. Then what principal component analysis does is to find the principal subspace. For example, here in this two-dimensional data, if you wanted the one principal component, you're going to find this one blue arrow, assuming that, again, that the data is 0 mean, such that when you project every data point down onto the subspace, so that now you're approximating every data point by its projection on the subspace, then the error that you make through this approximation, which is basically this black line, the sum of the squared errors that you make over the entire training data is minimized. So again, we are finding this principal subspace such that when we project every training data point down onto the subspace and replace these data points by their projections on the subspace, then the squared length of the errors that you will make is minimized. That is principal component analysis. So I'm trying to animate it here. You have a bunch of zero-centered data, and we want to find this principal subspace such that when you project everything down onto the subspace, the squared length of the sum of the squared lengths of the error is minimized. So basically, you sort of search through all possible subspaces, and after scanning through all possible subspaces, you sort of arrive. How do I make this animation go again? You sort of find the one where the squared length of all of those black lines is minimized, and that is now your principal subspace. That is principal component analysis. So we can do this in closed form. Although in theory, this is really a search problem. Finding principal components is a search problem, obviously, right? I'm searching through all of these guys, and I've got to find out which of these gives me the lowest error. For which of these guys, the squared lengths of all of those black lines is minimized. It's a search problem. But then, because we are looking for nice squared lengths, it's an L2 quadratic L2 error, we can find a closed form solution. So let's say the principal subspace has this basis W, which is a unit vector. Then you can find the length, you can find the projection of the vector onto the principal subspace by just taking the inner product between X and W, which is X transpose W. So the length of this guy, the length of this error is going to be the length of X. This is Pythagoras theorem. The squared length of the dotted line is going to be the squared length of the blue line minus the squared length here. So it's going to be the squared norm of X minus the squared norm of the projection. This is the error that you make for any given data instance when you project it onto W. So I can expand it out. And so when I actually do the perform principal component analysis, this T should be a superscript. I keep fixing it and the error keeps coming back. Anyway, I compute the squared length over all of my training data and I minimize it. And when I compute the squared length and I minimize it, I end up with a standard eigenvalue equation, which I can solve to find the principal subspace. This is the technique that all of you are familiar with for principal component analysis. But then there is also an iterative solution. Let me actually skip the math, right? So here's what I can do. I can also give you an iterative solution for principal component analysis. Here's what I can do. I can initialize my subspace, my guess for the subspace, which is basically initializing the bases within the subspace. And that's maybe this red line, right? And then I'm going to project every data point down onto this red line. So this black one is now going to be approximated by this red dot. This black line is going, this black vector is going to be approximated by this red dot, and so on. When I project it down, what I'm really doing is finding the closest point on the subspace to this vector. That's basically the point which is perpendicularly below the vector. I just have to find the perpendicular drop onto the subspace, and that is my projection onto the subspace. Now here's the interesting bit. Suppose I attached this vector to this red dot. I attached each of these vectors to the red dot with a string. And the string has an elastic tension which is proportional to the squared length of the dotted line. And now I just let it loose. This vector is now able to pivot around this point. It's allowed to rotate. And if I simply let this vector loose and I say, okay, I want you guys to sort of figure out such how to rotate the vector such that the total tension in these lines is minimized. Do you think the vector is going to remain the same, or is it going to rotate? What would happen? I mean, think of this as a physical problem. I've attached all of these balls with ropes to this
It's going
this
to.
line. Pardon me?
It's going to rotate.
It is going to rotate. It's going to rotate to something like this. And once it rotates, these lines are not necessarily going to be perpendicular to the axis, to the basis, right? It's going to find the position where the total tension in all of these lines is minimized.
Oh.
Right? Yes, no.
So the point on that line that was originally there, it was perpendicular at that time, but when you rotated it, the attachment was fixed. So
yeah. So when you minimize the tension, you're allowed to rotate it and maybe stretch the line, right? So it's going to end up finding a new position of this kind.
Okay. And those lines are not necessarily parallel either. They're unique to the points.
That's it, right? And then now I can drop a new perpendicular, tie them up, and then let it rotate and stretch, and it's going to find a new point. And I can keep doing this, and eventually it's going to end up with at a position where the whole thing is kind of stable. So that's an iterative algorithm for PCA. I tried to animate it, and MATLAB gave me this miserable figure. So I'll show it to you anyway, just because it's psychedelic, but I need to fix this. So now here's a cartoon view of iterative PCA. Here's what happens. I start off with an initial guess for my subspace, right? Then I'm projecting every data point onto the subspace. When I'm projecting the data point onto the subspace, literally, when you've got an L2 loss, what you're doing is multiplying X by the pseudo inverse of the basis matrix. So that's going to give you this position Z on the subspace. Now then, given the, actually no, so this is, yeah. Now given this Z, this is like attaching each data point onto the red ball. I'm letting the subspace rotate and stretch. So now I'm going back and estimating W. And so iteratively, just if I draw it differently, here's what I'm doing. I start off with an X, I get an initial estimate of W, and I find the closest point Z on the plane for each X. Then I attach the X to the Z, and then I let the plane rotate. So I re-estimate W such that the total tension is minimized, right? But what I'm really doing in that case is that I'm reducing the total error between the projection and the position on the plane. So in this whole process, when I first estimate Z and then go back and re-estimate W, I'm trying to come up with this reconstruction X again, going back here, what happens is that when this plane rotates, over here, right? I go from here, and when the plane rotates, the total squared length of those lines is reduced, which means that the projections are now closer to x on average than they were at this point, right? The red dots are closer to the black dots on average than they were initially. And then with the new projection, again, the red dots are closer still to the black dots, and then it keeps rotating. So at each step, this is minimizing the error between the point on the plane, this should be x hat, and the original data point. But then when you look at this figure, this is just an autoencoder, right? I have an encoder which goes from x to z. I have a decoder which goes from z to x. And so this whole thing is just an autoencoder. And once you see it as an autoencoder, you can actually use backprop, which minimizes the error between the output x and the input x, to first estimate w, and then using this resulting z to and then estimating the encoder. So this whole thing, this is the relationship between PCA and autoencoders. Autoencoders with linear activations are performing PCA because, as you can see, this process is just PCA. So any questions so far? Questions, anyone? Did you get this? Raise your hands, guys.
I have a short question.
Yeah.
So why, like I get the iterative part, but why are we like rotating it? Like, why does that like get us to like the final thing that we wanted?
So remember what we are doing. So the basic problem we are solving is trying to find this plane which minimizes the squared length of these lines, right?
Yes.
So now when I just initialize this and drop everything on this, I'm going to get some squared lengths of these lines, right?
Mm-hmm.
Now, if I attach these guys to these red dots and just release this plane and let it rotate and stretch to minimize the tension in these lines, it's going to get to a new position where the squared length of these lines is reduced with respect to this position, right?
Mm-hmm.
Right?
Oh, you meant like reducing? Okay, you get this new line by minimizing like the thing that you just drew.
Yeah,
Okay.
basically I'm minimizing. You can think of these as elastic lines, and it's going to sort of find a new position where the tension is less, right?
Mm-hmm.
And so now, but then when I drop a new perpendicular, these points are closer still to the black dots.
I see. Okay.
And then I can and now I can attach it, and now it's going to find a new point. And it's going to, I can keep repeating it till the whole thing stops doing and it stops moving, right?
Okay, cool. Makes sense. Thank you.
Yeah. But when you write it that way, this actually ends up being an autoencoder. It's very pretty, right? But there are a couple of different problems over here, right? So here's, I don't know if you guys can see my screen, see this sheet of paper. Can you see the sheet of paper?
Yeah.
Okay. So regardless of whether I've got the sheet of paper like so, or whether I rotate it like so, the perpendicular drop on the sheet is the same, correct? It's going to be in a different position, but the actual, so if I held it here, this some dot here is going to fall onto this position. If I rotate the sheet, some dot here over here is going to fall in a different position on the plane, but the length of this error remains the same. Does that make sense?
Yeah.
Okay. So also if I stretch this sheet of paper, that doesn't change the length of the error. That makes sense? Guys?
Yes, it makes sense.
Right. Okay. So this means that when I learn this autoencoder or when I perform principal component analysis, this W matrix, which are basically the bases of my subspace, the answer for that is not unique. So long as they represent the same plane, I can generate the plane in many which ways by rotating and stretching it in the same position. And they're all giving me an equally good answer as far as the minimum projection error is concerned. And so you don't have a unique solution. We need some way of, the estimation is, I can stretch the space, so the estimation is scale invariant. I can rotate the space, and the estimation is rotation invariant, which means that I have many different solutions, right? So we can find a unique solution. To find a, now if you want to get a solution, clearly saying I have all of these solutions is not a very satisfactory thing. You want to get one answer. So out of all of the infinite possible rotations and stretchings of the plane, how do you choose just one? You want one answer, right? And so in standard PCA, you make an assumption. You're going to say that I want my bases to be unit length. I want them to be orthogonal to one another. And that is going to give you the standard eigenvalue problem, which you're familiar with for PCA. But there's a second way of getting a unique answer here. And the second way is to say that when I begin dropping my data points onto the plane, I want the scatter of the, so remember, when I, if I've got some, if I've got some, in some three-dimensional space, so if I've got some two-dimensional plane, every data point gets dropped on to a position on the plane, right? So, and the position on the plane is sort of expressed in terms of the coordinates on the plane itself. And I can just put a different constraint. I can say that I want the variance of the position on the plane to be unity. So what do I mean by this? This may seem kind of abstract, but it becomes much cleaner when you look at it in terms of the autoencoder format. So here's what we had. I'm saying that in the iterative solution, I go from X to the position on the plane. Then from the position on the plane, I go back and let the find a new plane such that the error is minimized, right? Now your standard PCA is going to want this W to be an orthogonal matrix. All the columns are unit length and orthogonal to one another. And that gives you one unique solution. A different solution is to say that I want the variance of this Z to be a standard Gaussian. And that too will give me a unique solution. So how do we do that? To see this, let's go back and look at what we were actually doing when we performed PCA. I had all of these vectors. And if I knew the position on the plane, the projection on the plane for each of these vectors, then I could find the plane. But I don't know it. So what we do is that we initialize the plane, or rather the basis for the plane, and then we found the position on the plane for each of the vectors. Then once we found the position on the plane for each of those vectors, we use this completed data to let the find a new plane, and then kept re-estimating this, repeating this process, where in each step, we had a plane, we found a position on the plane, which is the Z, then use this completed data to find a new plane. So what does this look like? Guys, what does this look like? We've just been through this.
It's maximization, like EM.
It is EM, right?
Yeah.
In fact, it is EM. But what is the generative model over here? What is the distribution it's encoding? Here's what we have. Imposing the constraint that Z must have unit variance is the same as assuming that Z is drawn from a standard Gaussian, right? And so the decoder of this guy is basically just a generative model. You're saying I'm drawing a data point from a standard Gaussian and putting it through the decoder to generate my new vector X. And so the generative model behind PCA is this. This is basically a PCA, remember, is a linear autoencoder. We are saying that in order to generate any data point X, we have a principal subspace. We first take a Gaussian step on the principal plane, and then we take an orthogonal Gaussian step perpendicular to the plane, and that gives us the data point. So the overall generative model for linear autoencoders is that we assume for PCA is that we assume that data are going to be that there is a principal subspace. In order to generate a data point, we first take a Gaussian step on the principal subspace, and then we take a step at 90 degrees of that principal subspace. And the length of that step is also Gaussian. And then the point we arrive at, that is our data point. So the objective of PCA, or learning in the case of linear autoencoders, is to find this principal subspace. So here's the generative story for PCA. Z is drawn from a k-dimensional isotropic Gaussian. The Z is now transformed using your basis matrix, which we represented as W earlier. That's going to give you a position on the plane. And then we draw a Gaussian noise, which is orthogonal to this plane, and you add it. And that gives me my generated data point. And the noise itself is assumed to be zero mean Gaussian. And the step over here is also assumed to be a zero mean Gaussian. So the overall distribution is going to be Gaussian. And when we perform PCA, what PCA is actually doing is computing a maximum likelihood estimate of the variance of this off-plane step and the maximum likelihood estimate of the bases for this plane itself from the training data. And so here's the generative story for linear autoencoders for PCA. This is, you first generate X from a Gaussian distribution, you put it through a linear transform, you get a new value, you add some noise, which is orthogonal to this guy, and you get a new, and then you get your data point. So this is your decoder, and the decoder, where the input to the decoder is assumed to come from a unit Gaussian. This is a generative model. And the encoder of the Gaussian is simply trying to find, given a data point, the position on the plane. So when you put through this entire autoencoder has two steps. The encoder portion tries to find the position Z on the plane, and the decoder generates the data point from the position Z on the plane. So the encoder transforms this input X into a Gaussian variable Z, and the decoder transforms this Gaussian variable Z onto the principal subspace reconstruction. And so because everything is Gaussian, the distribution that PCA models is also Gaussian. You have a Gaussian variable being linearly transformed, you're adding a Gaussian to it. The result is still going to be Gaussian. And so the result says that the distribution of the data is a Gaussian that lies very close to a principal subspace and consists of data, a Gaussian data on the principal subspace plus Gaussian noise orthogonal to it. That is the distribution that's modeled by PCA. Now, here is the thing. PCA always assumes that the noise is orthogonal to the data. It says that in order to generate the data, you're first going to take a Gaussian step on the plane, and then you're going to take a Gaussian off-plane step, right? Now, if you think of this as a model for real-life data, it's kind of hokey. PCA is fundamentally broken in the sense. Think about sounds. If you just, if nobody is speaking in the room, and if you just close your ears and listen, and you listen to the sounds in the room, you can hear ghosts, you can hear music, you can hear stuff. Random noise sounds like meaningful sound. Similarly, look at random dots or Rorschach tests. Those things look like real stuff. You can see faces and clouds, you can see dogs, you can see cats, you can see stars. Noises and images also look like noise and look like images. So it is not true that in real world data, the noise is always orthogonal to the data. That's not the case. So I can generalize PCA by saying that when I add noise to this linearly transformed Z, this noise is no longer required to be at 90 degrees to the subspace, but the noise can be full rank. It can be in any direction. And so this is the updated version of principal component analysis, what we call the linear Gaussian model, where Gaussian noise goes into this linear transform, and then you add full rank noise to it to get an output. And so the only thing we're going to assume that is that this full rank noise has got a diagonal covariance matrix. And so this is our linear Gaussian model. And if you know the principal subspace, the linear Gaussian model differs from PCA in one very key way. In PCA, if I give you the principal subspace and I give you the data point, there is only a unique way of generating the data point. So basically in PCA, if I told you that this is my principal subspace and this is my data point, then there's only one way of generating the data point. You have to first come to this point exactly perpendicularly below this data point and then go up to it. So there's only one way of generating a data point. In the new model, you could also have come here and then taken this step. You could have also gone here and taken this step. Because the noise is no longer required to be orthogonal to the plane, the way to produce any data instance is no longer unique. And so this is still a parametric model for a Gaussian distribution. And the parameters are still the parameters of the plane and the covariance matrix of the Gaussian noise that you're adding. The only difference is that, and this is in fact what is known as factor analysis. A is known as the loading matrix, D is a diagonal, and the position on the plane Z is what is known as the factor. And the key problem is that the way of the manner in which you generate data is no longer unique. And so you will not have closed form solutions using standard assumptions like you do in the case of PCA. So here's the story for the day. EM is an iterative technique to estimate probability models for data with missing components or information. PCA is actually a generative model for Gaussian data, where data are assumed to lie close to a linear manifold with orthogonal noise. And linear Gaussian models or factor analysis is a generalization for PCA, where data are still assumed to lie close to a linear manifold, but without directionality constraints on the noise. The noise is not required to be orthogonal to the principal subspace. And so this is where I'll stop. I'll stop the recording. Thanks for your patience for being here. And if you have any